questions for this? All right, so let me say a couple words about this. Number one, notice that I've got that number 2 to the 32 power plus 1. Anytime that 2 to a power of 2 power plus 1 turns out to be prime, it's called Finite prime. And these were, it was conjectured early on that these were always prime. This turned out to not be the case. And I think this is the smallest one that they actually first determined it's not a prime. This is, of course, before the days of computers and calculators. This is like, you know, like 100, it's like 600 billion or something like this. 2 to the 32 plus 1 is not a prime number. It's the smallest sort of number of that form. 2 to the n plus 1 is not. Find its smallest prime divisor. And here's my hint on how to do this. To do it by hand, notice that if you have a prime divisor of 2 to 32 plus 1, if the prime divisor is large enough, then show that 2 to the 64 power is equivalent to 1 mod b. That means 2 to the 64 to the first power is 1 mod b. We have some theorems, including Lagrange's theorems and others, that will allow you to narrow down that search. Now that you know that 2 to the 64 power is equivalent to 1 mod b, if b is a large prime, tell me what that tells you, and you can probably find the smallest prime divisor that way. Number 2, so make me a little table or something like that. Explain yourself a little bit when you do this. For every number k between 1 and 20 inclusive, give an example of a finite ring. And here I want you just to restrict yourself to direct products of rings of the form Zn in finite fields. So it can be anything you can put together. A direct product of 2 finite fields, 2 Zns, a single Zn, a single finite field, or 3 Zns, whatever. And the Zns can be different values then, of course. So give an example for every number between 1 and 20, such that an example that has exactly k units. So, for example, let me get you started off. Z2, that has 1 unit. So we've got that leg. Z3 has 2 units, 1 bar, 2 bar. It's got that leg. Keep going. Give me an example for everything between 1 and 20. There are a few values that this can't be done for. So record those 2 and tell me why it can't be done. I think there's 3 values that it can't be done. So that ought to be, this will give you an opportunity to see kind of the unit structure, how you can make it work. And again, this comes up in coding theory as well. Number 3, you'll think I had a stroke with this first one, but this is actually this first one doesn't seem to be connected to the rest of it until the end, but it's connected. Suppose that G is a group, and suppose that A and B are elements of G. And for parts B and C of this problem, please refer to the diagram on the following page. I'll show you in a moment. Show that if A times B has finite order, then say the order of A times B is n. Show that if you reverse them, it's also got order. Number B, if we denote by x the act of rotating on the top level of the Rubik's cube 90 degrees clockwise, and by y we mean rotating the right side of the cube 90 degrees clockwise, then find the permutation induced by doing move the top, move the right on both sides of the corner pieces. And so, and there's my beautiful rendition here. So here's what I want you to do. If you turn the top clockwise, see the top piece, then the block that I labeled A, so the corner block, let's see which way it's clockwise. The block that I labeled A will go where? Yeah, it will go to E. The block E will go to F. The block F will go to B, and the block B will go to A. Right? And at the same time, the side blocks, 1 will go to 4, 4 goes to 3, 3 goes to 2, 2 goes to 1. Right? So what I want you to do is rotate that top clockwise and then the right side with VCGF clockwise. See what the permutation does to those corners, right? Write it down for me. See what the permutation does to the sidewise as well. Then part C, the follow-up to that is how many repetitions of X, Y must be performed for the cube to return all of its pieces to their original geographic locations. I only care about the blocks getting back to where they originally were. I don't care if they're rotated or spun, anything like that. And D, answer the question C for the move. What if you do it in the other order? Okay. Any questions on that? Well, so what you'll do is, for example, what did I say? I said clockwise on the right, didn't I? So for example, now remember, when I turn, what I said, turn the top first and then the right, that means I'll write it in the opposite order. So if I want to get the permutations right, I've got to do it in the other order. Because remember, we do it like function opposition. Okay, what does the top do to the corners? Where does A go? Which goes to F, right? Which goes to B. Correct. Yes. And now what happens when you turn the right side clockwise? When you think about clock for a minute. B goes where? Agreed. To. Now just multiply this out like we were doing before. And that'll be the permutation. Multiply that. And do the same inside. Other questions? Okay. Okay, so the last bit before we get all into on the applications is finite fields. I left you last time with a question. Did anybody figure out, was anybody able to find a field of order 4 or 6? Actually, that's going to be very important. In fact, we'll find out that there is a field of order 4. In fact, there's only one of them. And I'll show you what it is. It is impossible to build a field of order 6. And we'll see that. First, I've got to tell you something here. And this is something that we haven't attached the words yet, but we will now. So suppose R is more generally a community frame. One, the characteristic R, which is somehow the right way. Smallest positive. In. it is the smallest positive integer n such that when you add the identity of the ring to itself n times, you get 0. Now, let me finish my thought here. Let me put this example. If no such positive n exists, we say characteristic R is equal to 0. Can anybody think of a commutative ring with one that has characteristic 0? Can you think of a ring where no matter how many times you add 1 to itself, it ain't never going to be 0? What's that? No. It doesn't have to be a finite ring. How about the integers? Good idea. No matter how many times you add the ordinary 1 to itself, it ain't never going to be 0. On the other hand, can you give me an example of a ring of characteristic n for any n? There you go. A second. Very good. This one's 6. You can do this directly, or last time, I believe it was last time, we noticed this ring was isomorphic to 6. Let me point out, following the theorem, and by the way, I haven't proved for you that such a finite field ever exists yet, but we'll get there. And I'll build something for you. Note, P is a finite field of P elements. Characteristic P here is yeah. Characteristic of that always has to be private if it's finite. 2, any finite field must contain CP as a subfield. And number 3, and this is kind of the interesting one here. How many elements can there be in a finite field, right? I left you with the teaser last time. I said, see if you can find me a finite field with 4 elements, because we already, I know I can find a finite field P element for anything. You find me one 4, you find me one 6. This theorem shows that it's feasible to look for on the six. Any finite field has exactly n elements for some natural number. So you can have a field of order p squared, p cubed. No way are you ever get a field of order six. You can't do that. So this is let's show what this is. And these are kind of built on themselves. Can you explain what the characteristic? I think I actually previously in the class we actually sort of discussed this a little bit, although it may have been couched in slightly different terms. What do you suppose the characteristic has to be? Well, let me point out first thing. If it's finite field, then n times 1f 0. So I know that the characteristic is not zero, right? Why is this true? Because just start writing down 1 plus 1 plus 1 plus 1. Eventually you have to repeat yourself. And so when you add a finitely many ones, you have to be zero. Everybody agree with that? But the question is why does that n have to be prime? Suppose it's not prime. And I'm going to show we get a no-no for that. This can't happen. Well, what does it mean for n to not be prime? Well, it means that I can factor it with factors that are bigger than 1 and less than n, right? So AB with those factors strictly between 1 and n. Agree? But here, what do I mean by AB? I really mean A times 1F. Right. I just mean add 1 to itself A times, add 1 to itself B times, and add them up. This is the same thing as n times 1F, which is 0. So notice that A and B are not 0 because A1F and B1F are not 0 because A and B are smaller than n. Everybody agree with that? But AB is 0. And this is a contradiction. Those fields now have 0 positions. Because everything is not 0. Well, let me rephrase. Fields cannot have non-zero 0 positions. Because every non-zero element is unit. Yes.
So something, but in the third example, there is 6.
What's that name?
In your third example,
Yeah.
Characteristic 6.
Yeah, the characteristic 6.
Oh, right.
But this isn't a field.
Oh, yeah. Oh, so it's only fields.
That's right. Fields have to have characteristics prime. This thing, this is a field, that is a field, but when you put them together, it's not a field.
The example above C of n.
The characteristic of Zn is n, but if n is not prime, this isn't a field. For exactly this reason, because you'll have 0 positions. Okay, first time over. It turns out that the characteristic has to be prime. 2. Okay, any finite field contains 1, right? Once you've got 1 bar, you've got 2 bar, you got 3 bar, you got 4 bar, all the way up to P bar, which is 0 bar. So there's your little copy of C mod P in there. Just whatever 1 generates. 1, 1 plus 1, all the way up to 0. All right. So there, 1 and 2 and 3. So ZP is a subfield. Yes. The characteristic is the smallest positive integer, such that when you add 1 to itself, that many times you get 0. Now, this one's like a big mystery. Anybody? Okay, so all right, here's what we have so far. I know the characteristic is big. I know that it's contained in there. But see, that's also true of Z2 cross Z2, right? If you have just Z2 cross Z2, it's got characteristic 2 and it contains Z2, but it's not a field. It's also got 4 elements, but it's not a field. How do I know that field has that PV elements? This is actually a really cool application of 3110. Yeah. Vector space. So F is our finite field. You know it contains CP. I claim it's a vector space. What do you have to be a vector space? Well, the first thing you got to have is you have to have that. What you remember all that crap in 3110, right? You take 2 vectors, you add them up to get a new vector. Every vector has a negative vector, and you add the vector to the negative vector, and you get the 0 vector, and the 0 vector adds up and doesn't change anything, and so forth, right? They didn't tell you this in 3110 at the time, but all that means is a vector space is an abelian group. Bang. This takes care of all the additive things. Sum of 2 vectors is vector. You've got the 0 vector. The 0 element of the field is the 0 vector. Right. What else does the vector space come equipped with? Right? I mean, a vector space wasn't just an abelian group. You went through all the stuff about adding the vectors and subtracting them and the 0 vector and all that. But then there was another bit of structure on vector space. What else did you do? Could you multiply 2 vectors?
Scale it.
Now, you couldn't necessarily multiply 2 vectors, but you can multiply by a scalar from the field, right? You always had that real number alpha that multiplies your vector. You got that crap here too. But B and F, I say that to emphasize you can think of it as a vector, and alpha being CP, alpha B is in F, right? Because alpha is in CP, which is contained in F, so this product is in there because it's a field, right? The product of 2 things is in there. And it works just like scalar multiplication. What are you supposed to have? Well, you're supposed to have like alpha beta B is alpha beta B. Got that. You gotta have alpha plus beta B equals alpha B plus beta B. Got that, right? I mean, this is just distributive law. Like it's a ring. Oh yeah, you need 1 times V equals V. Ah, no problemo. Got that. So this is actually vector space. Now, one more thing.
Question about output.
Mhm.
Is that
No, it's just the ring properties. It's the product of 2 elements of the ring or so in
Okay.
there, right? Because these are fields, and actually, fields only have 2 ideals: the 0 ideal and the whole thing. So a field only has 1 property. Now, what's the big thing that probably drove you out of your ever-loving mind when it comes to vector spaces? What do all vector spaces have? Try to base your answer on what happened in 3110. Any vector space has a basis, right? Remember all that business about linear independence, right? You talked about R3 and R2 and so forth. A vector space has a basis. I'll go you one step further. My basis has to be finite. Anybody tell me why I know for a fact that my basis for F, my basis elements is only going to be finite to many of them? 3110, everybody, like, I know, we're in therapy and all that. So remember, a basis is a linearly independent set that spans it, right? Right. So, like, for example, in R3, so we'll do a quick review here. Because any 2 vector is, take your favorite 2 vector, AB. It's A times this, B times this, right? These 2 are linearly independent and they span. R2 has other bases too. 1, 0, 1, 1, right? Or, let's see if I can do this right. 1, -1, 2, 3. Any set of 2 linearly independent elements will span R2. Right? Remember all that business where you put the columns or the rows in there to determine it was not 0, it was a linearly independent set. Because this sparks some stuff from way back in the day. So a basis is a small, it's a way to efficiently write every element of the vector space, right? So I can write everything in R2 as something times this plus something times that. That's what a basis is. This has to have a basis. Can somebody tell me why? For sure, I know it's a finite basis. There's a silly reason. That's right. F has only finitely many elements, so I can certainly span F by just using all the elements of F. Right? That's probably way too much because I'm sure that those, if I could guarantee you that won't be a linearly independent set, but we can whittle it down until it is a linearly independent set to span. Right? So this basis is finite. Let's say V1, V2, Vn. Agree? So let's suppose the dimension of the vector space is n, right? By the way, notice if n equals 1, then it's got a basis of 1 element, and my finite field is CP. So that kind of comes full circle, right? If there's only one basis element, that means that it's just CP. In general, can be written uniquely in form alpha 1 D1 alpha 2 D2 alpha 3. And if those, when you all did, in linear algebra, when you did like change of basis and stuff like that, oftentimes you would write this in vector form. Sometimes this is written, this way, alpha 1, alpha 2, alpha n. So we consider this an n tuple of elements, where the alphas just designate the multipliers needed on the various basis elements. Everybody okay? So now we know everything in F can be written uniquely in this form. The choice of the alpha i's uniquely determine this. So how many elements in F? Well, ask yourself this. Ask yourself, so how many choices do I have for choosing the first entry here? Where do the alpha i's come from? They come from ZP, right? That's the field that we're over. How many elements are there in ZP? Here. How many choices do I have for the second coordinate? So forth and so on. So any finite field. That's a little bit of magic. And that actually shows you the power of linear algebra to reach out into something else. The realm of finite fields and curves. Okay. Everybody has seen finite fields because you've all seen CP, right? We know what CP is. We know it's a field because every non-zero element, it's a finite ring, and every non-zero element is a unit, so it's a field. But probably what you haven't seen is a finite field for higher powers. Right? So, for example, I did say that there's a field of 4 elements, and I'm going to show that to you. Let me give you this theorem, and then we'll build some of these things. Theorem. By the way, let me point something out at this juncture. And this is the way things work in mathematics. What I have shown you is we know that there for every prime there's a field of P elements, right? Z, we got that. We've also shown that if there are other fields of characteristic P, they have to have P to the n element, right? What we have shown is if there is a finite field, that's its size. I haven't shown you that they exist. Other than for the case n equals 1, we don't know that these even exist. This theorem tells you. But P prime and n be any natural number, then there is a field. And in fact, my next statement says basically there's only one. elements is unique. What that means is if you've got a field of order 9 and you've got a field with 9 elements in it, those two fields are essentially the same. There's a function one-to-one and onto between those. This one is a little I'm going to do this kind of out of order here. For Mark 7-6. I'm going to describe in this remark how I'm going to build these for you at the moment. I'll build a couple of small ones and I'll let you play with it because it's kind of fun to play around with these things. They code in a lot of information. Seven, three, four. Yeah. By the way, how many roots do you expect there to be of a polynomial? This polynomial, I would expect there to be p to the n roots, right? Because that's the root of the polynomial. Now, you'd also, and it turns out that all the roots of this polynomial actually are all different. So this will actually give, and I'll show you how to build this in a moment. Let me give you one more proposition and then we'll construct some of these. Proposition 7-5. Let F be a finite field. P the elements. And, B, numbers. There is an irreducible polynomial. Degree n. The proof of this is beyond the scope of what we're covering here. What this means is if you have any finite field you want, and you walk up to me, give you a number, 1, 2, 7, 43, whatever, I can find you a polynomial with coefficients in that field that you can't reduce. It can't be broken down into smaller polynomials. And this is actually, I write that down because that is another way that you can construct these things. So let's look at some examples here. I'm going to construct these over C2 just because it's easier, but you can construct these over larger fields, C5, C7. You can go crazy with this. So I'm gonna construct the field kind of from first principles, and then I'm gonna invert the process over here. Okay. I'm gonna list all possible quadratic polynomials. By quadratic, I mean, I've got the square term in there, no higher term, right? Notice that I've got a constant term and a linear term that can be either 0 or 1, so there should be 4 of these. Everybody agree that that's an exhaustive list of polynomials. Only one of these is irreducible. Can you tell me which one? Only one of these polynomials cannot be factored down any further. It's kind of confusing. Can somebody tell me for sure? I see 2 that I know are reducible that can be factored. Right, I'll throw these off because, so if there's an irreducible one, it's got to be one of these 2. Well, remember, this has to factor over C2, right? Let me show you how to do it. That's actually x plus x squared. What happens when you multiply this out? This is x squared. The 2 is 0. Poof, it's gone. Right? Notice for quadratic polynomials, all you have to do to see whether it factors or not is to test if it's got a root. This works for quadratic and cubic. It doesn't work for higher degree polynomials because a 4th degree polynomial might break down into 2 quadratics. But all we got to do is test to see if this has got roots or not, right? Because if this factors, it's either got to have a factor of x or x plus 1. Well, let's just test. When I plug in 0, is that a root? When I plug in 0, I get 1, right? So x is not a factor, which is pretty obvious. When I plug in 1, I get 1 and 1 and 1. 3 is equal to 1, so not a root. So this was actually irreducible. Everybody agree with me?
Show 0, 1, because
That is correct. And those are the only things that I can plug in, which is another reason why I started with C2. It makes my life a little easier. There is a fancy math construction for this, but let's let omega be a root. Notice that omega is not in C2. Because after all, I tested everything in C2 and it didn't work. So what does this mean? This means omega squared plus omega plus 1 is equal to 0. If it's a root, and another way to write this is omega squared is omega plus 1. Now, before you all pick on me about my signs, let me point out that since this is C2, this is in characteristic 2, a plus and a minus are the same thing, because 2 equals 0. Let me show you how this field works. Again, it's a vector space over Z2, and my basis is 1 and omega. So the elements of the field, elements are 0, 1. I'm going to put bars on it. Omega and omega plus 1. And since I know how to add 0 to everything, let me do an addition here. Here's how the field works. 1 plus 1 is 0. When you add anything to itself, you get 0 because 2 equals 0 here. 1 plus omega is omega plus 1. 1 plus omega plus 1 is omega. Omega. Everybody see how the addition works?
So it's just like subtraction, basically.
Addition and subtraction are the same thing because 2 is equal to 0. That's right. In this particular field, that's why it was convenient for me to start with Z2. Even for Z3, it's a little bit harder. Now, how does multiplication work? If I multiply anything by 0, I get 0, so I'll leave that out. And 1 times anything is itself. Now, what's omega times omega? Well, it's omega squared, letter B, but that's equal to omega plus 1. Right, because of this identity here. What happens when I multiply omega times omega plus 1? I get omega squared plus omega, which is 1. And look at that. This means that omega and omega plus 1 are inverses of each other, which is what I need in a field. Just looking at the table, anybody want to predict what this should be? What are you supposed to miss in block is? Just by looking at the table, can you take a guess? I agree. I think. Well, let's see. Omega plus 1 squared is omega squared plus 2 omega plus 1, which is omega squared plus 1, which is omega. Again, using this identity.
Is one the same as -1 in this field?
Yes, 1 and -1 are the same thing in this field. Now, check it out. X minus omega, X minus omega plus 1. I can use my multiplication and addition tables to figure this out. This is X squared minus, and of course minus and plus are the same thing. This is X times omega plus 1. And reading my table, this is X squared plus X plus 1. Agree? Because omega plus omega plus 1. So those two things, as multiplication tells, are the roots of this polynomial here. Omega and omega plus 1 are the roots. And notice X minus 0 times X minus 1 times X squared plus. This part is X squared minus X. And this is X squared plus X plus 1. And when I multiply this out, I get X to the 4th. The X cubed terms are gone, the X squared terms are gone, minus X. And if you remember that polynomial, I said that's what happens here. So let me start you off on another example. What if you wanted to fill with 8 elements? Well, let's start actually. It should be all the roots of this polynomial here. There should be 8 roots. Now I notice that there's a factor of X. And notice when I put in 1 here, and it's 0, so there should be another factor of X minus 1. And some what's left over here. This should be X to the 6 plus X to the 5 or well, I know that when I plug in 0, I get 0, so that means it's got a factor of x. To this one, I know that when I plug in 1, I get 0, so that means that's got an x minus 1 factor. And I just factor this out. Notice it pairs off. This is x to the 7, then all the middle terms cancel because of the minus. And then minus 1 again. Is this irreducible? It's actually not. So here, we'll go over this next time, but you can actually factor this. And because I know it factors into cubics because of this. Should factor like that. Now remember, this is divide 2. So I'll leave it to you to check that for next time, and we'll talk further about this. But 1, 2 roots right here, 1, 2, 3 from this, 1, 2, 3 from this, that gives you 8 elements in this field. But check that factorization works. See if you can figure out what the addition and multiplication is. Any questions? Any questions out there? All right. Well, sometime next week, it might be good. If you can't get to class, send me an email, but it might be good to come to class because I'm going to dole out Rubik's Cubes for you guys to play with for like a week and a half, which unfortunately I will be back, but it's kind of hard for me to give them out of Zoom. So let me know if you have a hard time getting to class. All right, I will see you all next time.